Hello, my lovely students. Sorry for not doing this yesterday or earlier today. So we have that last full Riemann sum question. So these questions have a whole lot of moving parts. It's very similar to when we learned about the long derivative. There was a whole lot to it, and then eventually we got to the shortcuts. Here we actually kind of previewed the shortcuts. All right. So when we are finding the area under a curve, in this case, it's described as the area between the function and the x-axis, over the interval from 0 to 2, those are x values, and they ask for right endpoint Riemann sums. Okay. So over here, I sketched a picture of the graph. So there's our function up top, and then I just put some arbitrary number of tick marks. So if we were splitting it into 5 pieces, we would have a starting endpoint or a starting point and end point. And then to split into 5 pieces, we would have 4 tick marks in there. Or we can think of it as I start at 0 because that is where we start. I go one width, then another width, then another, then another, then another. And each one of those anothers is another width, and we just do that until we get to n of them. So when we're doing 5 rectangles, we start at 0. We have our first right endpoint, second right endpoint, third right endpoint, fourth right endpoint, fifth right endpoint. So we can think of our starting line as our 0, and then all the other x values are just for however many rectangles we have. So that sequence of x values that they said, we have our starting point and our ending point, and then we have x1, x2, x3, and it'll keep going until we get to xn, because we're going to use that generic n case, so then we can make n go to infinity, and the rectangles will all be little tiny widths, and then poof, we'll have a lovely area under the curve. All right, so let's think about making these divisions. So when I go from x0 to x sub 1, and then x sub 1 to x sub 2, the width, the distance between those should be the same. I want all of my rectangles to be equal width. The heights will be determined by the function. I'll deal with that later. I'm just focusing on making all of my divisions equal width. So when I look at 0 to 2, and I want to split it into 3 rectangles. Then I have my 0, 1, 2, 3 marks, makes my 3 rectangles. And then to figure out the width, I take the full length of the interval, and then I divide it by 3, and that'll give me the width of them. It's not giving me my endpoint numbers, just how wide the rectangles are. So if I have 3 rectangles, my width is 2 minus 0 over 3. If I had 5 rectangles, I'd have 0, 1, 2, 3, 4, 5. And now my widths would be smaller because I have more rectangles, but I still do my same endpoint minus start point, and I just divide by however many rectangles. So this is why the book had the delta x formula that we can use. It was delta x, which you just want to think of as the width. Delta means change in x, so it's how over do we go until we hit a tick mark. So delta x is b minus a, when we're looking at the interval from a to b, over n, where n is the arbitrary number of rectangles we're picking. So see, 2 is our b, 0 is our a, And in these specific examples, n was 3 and then 5. So now I'm going to do it for the n rectangle case. So delta x will be 2 minus 0 over n. So just like with my 3 rectangles, I could see I'd get 2/3. So 2/3 is how wide the rectangles are. But it's not like every one of those tick marks is the number 2/3. They have a starting point to start from. So when I want to get my first x number and my second x number, I'm looking for these actual tick mark. How far is it from 0? Now, in this case, we're actually starting from 0. So it's going to make that first one like really nice. But if I look at like my 3 rectangles, so my x sub 0 is 0. X sub 1 is 0 plus 1 width. So my first tick mark is actually 2/3. Pure fluke because we're starting at 0. Our earlier examples, we were deliberately not starting at 0. So you could see there was like the start value and then you add the width. Now, if I wanted my next x value, I know it's 2/3 away from the previous one. And then the next one would actually be 2. If we do 2/3 plus 2/3 plus 2/3, 3 2/3, we get 2. So here, like I had my starting point plus a single 2/3. And then here I had my starting point plus 2 2/3. So I can abstract that if I was going to divide it into more. Remember, this is our A, this is our delta X, and then the 1, 2, if you look, that's our subscript number. We're actually deliberately wanting to see that number there because that's how sigma notation works. We have that indexing of the number, so we want to see that number where it's appropriate. So we go looking for 1, 2, 3 in our numbers that we're trying to come up with a formula for. So this works for right endpoints. Our formula for left endpoints would be a little different, a little more annoying, honestly. But since we are looking at right endpoints here, if I come back over, my x sub 1 is going to start at 0, and I'm going to have my arbitrary width, 2 over n times 1. X sub 2, my same starting point, but now there are 2 widths to add. So my x sub k still starts from 0, still has the same width, but I add k of them. All right, so we have our delta x and we have our x sub k formula, just extracted from a smaller sample and then moving to the arbitrary case. Now that that's in terms of k, we're going to start to think about the picture and looking at the rectangles and looking at how we construct the area. So this whole time, my delta x was my width. My x sub k are just the endpoint values. So these are position markers, the tick marks on the number line. So I have my rectangle width. I need my rectangle height. So the height here, if we go back to our picture, the height is coming from the function. So when we said right endpoints, I'm taking my x sub 1, and then I want to figure out how high I am at that point. How high I am is determined by the graph, which means it's our function value. It's the y value of that point on the graph. All right, so I have my widths. Now I'm going to do my height. And this is going to be f of x sub k. So our arbitrary tick mark number, I want to know the function value of that arbitrary tick mark number. That's going to give me each of my heights. And so now my rectangle area is width times height, height times width. The order doesn't matter. Fx sub k times our delta x. This is for one rectangle. I want to add all of the rectangles. So this is where sigma comes in. So we start at 1 because we wanted our first right endpoint. So that's not our 0 case. That's one width being added. And we're going to go up to n rectangles. And it'll be f of x sub k times delta x. Now, f of x sub k is going to get a little much. So I'm going to do that in a little side panel. So I have my x sub k formula, the 0, we can toss out. So 2 over n times k. So this is now asking us, what is the function value when I input, we can write it as 2k over n. So this is where we're very happy 0 is our starting point because I'm not putting in something with addition there. But I need to go find my function formula. Like all of this so far, the only numbers we were using was the 0 and 2 as the start and end point. Now I actually need the function. So that function is 7x squared plus 9. Now, I haven't had to do this as often in here, but remember, function notation is telling us how to manipulate x. It's giving us a process, some dance steps. So when I say f of x, I know that of means multiply, and I know some of us are still wrestling with that difference there. But think of it more like a process, like square rooting an x. So here, when we f the x, we do 7 times the x squared and then add 9. So I deliberately write my formula like this to hopefully make the distinction between the dance steps that is the formula and whatever we choose to put as the input. So this is knowing the floss, and then there's okay, now I'm going to make my elementary school teacher do the floss. Now I'm going to make the principal do the floss. Now I'm going to make the department secretary do the floss. What we put in, we choose, but the dance steps are predefined. That's what the function does. It tells us the dance steps. So here, my input is 2k over n. So I'm just going to put that into my function notation. So this notation here will be 7 times thing squared plus 9. My thing is 2k over n. All right, now we're just going to clean that up a little. So this squared, since everything inside is multiplication division, everything gets a squared. Remember before, and I said, be glad we don't have addition. If we had addition, then we'd have to FOIL. So this is going to be a 4 now, a k squared over an n squared. And then still plus 9. And then I'm just going to multiply the 7 and the 4. So 28 k squared over n squared plus 9. This is the formula for our rectangle heights. So now this is something I can take back to my sigma. So this is saying this whole thing is the same as that whole thing. So I'm going to put that whole thing in this spot. So I'm going to keep my sigma. And now in that spot, 28k squared over n squared plus 9. And then while we're at it, let's just go ahead and make the substitution for our delta x. Way back here, that was 2 over n. Okay, so our sigma here, we've got beautiful formula. Yes. All right. Now we're going to use that new sigma knowledge to start messing around with all this. Okay. So seeing sigma on a sum, like to me, I'm like, that's redundant and kind of hurts my brain. So I want to distribute the sigma, but there's another distribution I want to handle first. So that times 2 over n, I'm going to distribute that through first. All right, so right now we still just have one sigma. And this is 28 times 2. Here, I'll just write them. 28k squared over n squared times 2 over n plus 9 times 2 over n. Now again, if it helps you here to write 9 over 1, so that way you don't accidentally try to distribute a 9 across division. We don't distribute across division. All right, multiply the tops, multiply the bottoms. So 2 times 28 is 56. So I have 56k squared over n cubed plus 18 over n. All right. Now our sigma notation is a shorthand for adding a whole bunch. Well, here I've got two things being added. So sigma can distribute across the addition. So I can view this as two separate sigmas. So I'm going to have my first one, the crazy 56k squared over n cubed, plus my easier to look at 18 over n. Now, remember our k formulas, like, were all about what happens when there's a k in there. I put my 1 in my k, then I put my 2 in my k, then I put my 3 in my k. Anything that's not k, like, we can factor out. If it's being multiplied or divided, we can pull it outside, just focus on the k, and then put the stuff back together again. So our only k here is this k squared. So it turns out over here on the right, this 18 over n, there's no k there. So when we say do the sum of this thing from 1 to n, I'm going to do 18 over n first, plus another 18 over n, plus another, and I stop when I reach n copies of it. So if I am adding 18 over n times, that whole times, so this one we can write as 18 over n. We leave a 1 because we're factoring those out. Multiplication, our placeholder is a 1. So adding 1 n times is n. So this one plus 18 over n times n, we're just going to have a plus 18 hanging on at the end of our sigma, figuring it all out. Cool. I say cool because that's a constant and it has no ends in it. Because remember, our end game goal is to make the rectangles have an infinite number so they all get super skinny and we get a perfect estimate. So now we're seeing, all right, my area has 18 for sure in it. Cool. Now our sigma here, the 56 over n cubed has no k's, so that's like a constant, the same way the 18 over n was. I'm going to factor that out. So that's just going to come into play after we get rid of our sigma notation. So now I have the sum from 1 to n of k squared. So the sum from 1 to n of 1, of k squared, and of k cubed are given known formulas. K squared is like the weird one that I never remember off the top of my head, so I'm going to go sneak and look because Chris was darling enough to provide it. I don't know why the book wrote it in terms of I instead of K. Like, that honestly really bugs me. Like, everything in our process uses K. Why would you put I's? It's just confusing. So, boom. So whether it's an I or a K doesn't matter because notice the I's don't show up in the end result. As long as we are starting at 1, we get this result for any n. So I'm going to keep my 56 over n cubed. And this is saying the entire sigma of things squared is this entire thing. So I'm going to put some brackets and write that entire thing. All right. Oh, now I'd love to say 56 and 6 like perfectly divide, but they don't. But we do get 28 over 3 at least. All right, so we have 28 over 3 n cubed, and then times that whole thing. There's two ways to go about this, but the way that seems to make the most sense for most people is just to distribute it all out and then distribute through the division. The more creative way is to actually take the n cubed and split it into n times n times n. And then I regroup my multiplication up there so I have each product divided by an n. So if that like verbal description makes you go like, ooh, like feel free, run and play with it. If you're like, I have no idea what she's saying, we're just going to go with the standard distribution, multiply it all out approach. But y'all know me, I'm lazy, so I'm going to sidebar it. So the n times n minus 1, that is n squared minus n times the 2n plus 1. We're going to box it. So 2n times n squared will be 2n cubed. 2n times negative n will be negative 2n squared. And then we have plus 1n squared and minus n. All right, so the 6 was already taken care of outside. So this whole thing is just 2n cubed. 1n squared minus 2n squared is negative 1n squared, or just negative n squared, and then minus n. And still with our plus 18. Like, I'm going to put a little highlighter around it. Because when you do separate steps like that, it's real easy to lose that extra thing. So anytime you have a step you did separate, like put a little star next to it, something that visually makes you look and go, oh yeah, that was supposed to be in there. All right, so now we are going to distribute this ridiculousness through. So we'll get 28 times 2 is back to 56 again. So 56 n cubed over 3n cubed. And look at that, the n cubes cancel. Like magic, like on purpose. Yes, on purpose. So negative 1 times 28, negative 28 n squared over 3n cubed minus 28n over 3n cubed plus 18. So that is my sigmas are gone, my k's are gone, the i's were never even in there. This is now a formula that I can apply the limit to. All right. So let's bring that in, our official limit as n goes to infinity of this whole gigantic thing. So this front one here, we get 56 over 3 because the n cubes are going to cancel. N squared over n cubed, my bottom is bigger. This whole thing will go to 0, and this whole thing will go to 0. But the plus 18, it's a constant, so as n goes to infinity, it's like, I'm still 18, still 18. So our result is going to be 56 thirds plus 18. 18 times 3 is 54. So 54 plus 56 is 110. So 110 thirds. So that is how much area is under our ridiculously plus 9 parabola. $110. And that plus 18 we got here, if you think about the picture and I like do a horizontal cut where it starts, that would be 9 high and 2 wide, which is 18. So there is actually logic to the pieces we get. So if I took the 18 off and I took the plus 9 off of my graph, the area under the curve of 7x squared from 0 to 2 is 56 thirds. So that's why a lot of times the constants we're kind of like, meh, it's a constant. Because that's a number that we can add or subtract in pretty nicely. Whew. All right. Then we move on to new stuff tomorrow.